Out there in the cosmos, you kind of expect things to follow certain rules, right? A sort of cosmic order. But every once in a while, something pops up that just, well, it refuses to play along.
So what actually happens when one of the universe's most reliable timekeepers suddenly gets this weird, unpredictable heartbeat? Well, let's dive in and find out. Okay, so let's get right into it. To really wrap our heads around this cosmic rule breaker, we've got to first understand what a normal pulsar is and, how it's supposed to act.
Okay, picture this. A lighthouse on some crazy distant shore, spinning ridiculously fast. Its beam of light just whips across the ocean. From our boat, all we see is a flash, 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 every single time that beam points our way. That, right there, is basically a pulsar. It's the super dense, spinning corpse of a giant star, and it's blasting out these beams of radiation from its poles.
And here's the really wild part, their precision. These pulses are so mind-bogglingly regular that they act as some of the most accurate clocks in the entire universe. They're like nature's metronomes, just ticking away, almost perfectly, for thousands and thousands of years.
But of course, it's not quite that simple. They don't all tick in the exact same way. Astronomers have basically sorted them into two main buckets. You've got your older, drifting pulsars where the signal's pattern kind of predictably shifts over time, and then you have the younger, steady pulsars, which are, well, they're supposed to be just that, stable, solid, and totally predictable.
All right, it's time to meet our main character, Pulsar B1946+35. Now this thing is way out there, about 18,900 light-years away in the constellation Cygnus, the Swan. And when we first found it, it was a textbook steady type, the reliable kind, the kind you could literally set your cosmic watch by. Keyword there, was.
Because you see, when astronomers pointed the giant Arecibo telescope at it for a good long look, what they found was something else entirely. They found a cosmic Jekyll and Hyde.
Yeah, the data that started coming back was just bizarre. This supposedly steady pulsar, it wasn't steady at all. It was constantly flipping back and forth between two completely different personalities.
So for about 1,000 pulses in a row, it would be in this mode scientists call the red noise state. Just think of it like a radio signal that's full of static and fuzz. It's just messy, chaotic, totally unpredictable.
And then, boom, just like that, it snaps into its other personality. For the next few hundred pulses, it becomes the complete opposite. It enters this high Q state that is incredibly rhythmic, superstructured, and perfectly periodic. All that cosmic static suddenly clears up into this crystal clear, repeating beat.
So what in the world was going on here? What was this strange beat trying to tell us? Scientists really had to zoom in and decode the signal from this bizarre, rhythmic mode to figure it out.
Okay, to get what's happening, you have to understand the beam structure a little bit. It's not just one big blast of energy. It's got a strong central core beam, and then it's flanked by two weaker beams on either side. These are called the conal outriders.
Okay, so here's the crucial part. How these three components, the core and the two cones, were behaving during that weird rhythmic state. The leading cone and the main core, they were pulsing together, perfectly in sync. But the trailing cone, the one at the back, was doing the exact opposite. It was pulsing in what they call counter phase. So when the front two were bright, the back one was dim. And when the back one was bright, the front two were dim. And get this, it wasn't a pattern moving across the beam, it was a stationary flicker. Like someone was just flipping a light switch on and off, on and off.
And this whole thing, this incredibly intricate dance, this flickering on and off between the front and the back of the beam, it repeated with absolute clockwork precision every 18 seconds. That was the heartbeat of its strange personality, a perfect 18-second cycle.
Okay, so a flickering pulsar. What's the big deal, right? Well, how does all this create a massive problem for astronomy? Because this rhythmic flickering, and especially the fact that the central core was involved, it just completely flies in the face of the leading theory for how pulsars are supposed to work. You see, for decades, our best explanation for this stuff has been what's called the carousel model. I want you to picture a merry-go-round at night. The central pole has a steady, unmoving light on it. That's the core beam. And the horses going around are like smaller spotlights that rotate around that central pole. Those are the conal signals we see. Simple enough, right? But this model has one single, unbreakable rule. The core is the anchor.
That light on the central pole does not flicker. It does not pulse. It is supposed to be absolutely stationary, while all the other parts revolve around it. That's the whole foundation of the model.
And this is the moment where everything we thought we knew just shatters. The theory says the core is a stable, non-drifting anchor. But the reality for B1946+35, its core is pulsing dramatically, flickering on and off in perfect time with its canonic beams. The central pole of the merry-go-round is blinking. That is just not supposed to happen, at all.
You know, the scientists who found this, Mitra and Rankin, they didn't really mince words in their paper. They wrote that what they saw cannot be reconciled with the existing model. Now, in the very careful language of science, that's a bombshell. It's basically them saying, folks, the theory is broken.
So where does that leave us? Well, not with a neat little answer, that's for sure. It leaves us with a brand new and, frankly, a much more exciting cosmic puzzle to solve.
Look, B1946+35 is way more than just an oddball. Its strange flickering isn't a drift like we've seen in other pulsars. Scientists are actually calling it something totally new, a rapid, periodic emission pattern change. What that means is the entire structure of the pulsar's beam seems to be rhythmically changing its shape and intensity. It's a whole new kind of behavior.
And all of this leaves us with one final, absolutely tantalizing question. The old map we had for pulsars, it now has this huge blank spot on it, basically labeled "Here be dragons." So, if the old model is broken, what new physics, what strange cosmic mechanism that we haven't even dreamed of yet could possibly explain the mysterious rule-breaking heartbeat of this incredible star?